Good evening all. We will be starting our week 11 problem solving session. So, I'm Akhil. I'm a fourth year PhD scholar from IIT Delhi. I'm working under the supervision of Professor Dhanya. And I did my bachelor's from NIT Calicut in civil engineering. And then I completed my master's from in water resources engineering and management from IIT Guwahati under the supervision of Professor Srija Pekar. And currently I'm pursuing my PhD in IIT Delhi from the year 2022. So in the previous week's lectures, we had completed the flow routing. So basically, we have almost covered most of all of the hydrological processes which are a part of the hydrological cycle. Initially, we saw what is the hydrological cycle, what are the different hydrological processes that are an integral part of these hydrological cycles. Then we saw how we can model each of these processes, and then uh, we tried to model the precipitation. We started with precipitation, the atmospheric water. Then we move on to the evapotranspiration. Then we tried to model the infiltration. Then finally we were trying to model the flow routings. So, uh, in today's section, what we'll be going to deal will be entirely different compared to what we earlier did in the previous lectures. So, here we are starting a new topic that is it would be somewhat uh, less dependent on the previous, whatever that we are been covering in the previous sections. So basically, it is related to a field of hydrology called stochastic hydrology, right? So what that we already, while when we were discussing the types of hydrological models, we had given a glimpse of what is a stochastic model. We saw two types of model. One was deterministic model, and other was the stochastic model. So deterministic models are the ones which the there is no randomness. So we give some input, it will give the output. It's independent of the day or the time, or it is, for example, at a particular location, particular catchment, we modeled the rainfall runoff model, we modeled it. And for a particular day, at a particular time, same amount of rainfall inflow hydrograph, the rainfall hydrograph happens, the outflow hydrograph, that is the output would be the same. If whether it happens today, 2 days after, if the input is same, the output will be also same. But in case of stochastic models, there is an additional term of randomness coming into picture. That is, the same input can generate multiple outputs, right? So that is the main difference between deterministic model and stochastic model. Stochastic model, we always try to bring in the terminology called the uncertainty along with the data variables, right? So in hydrology, when we deal with such variables like precipitation, evapotranspiration, infiltration, so these all variables which we deal with, they all are like related with some uncertainties that will be there, right? So, for example, when we are dealing with a precipitation variable, there can be uncertainty due to the measurement. So there can be measurement errors, instrument errors can be there, there can be and also manual reading errors can be there. So these are some a type of uncertainty. And if we are trying to model this using this rainfall, which has some uncertainty. I mean, you have to model the runoff using this. The runoff that we are getting will be having the uncertainty that propagated due to the uncertainty that was already there in the rainfall. And also, there will be model uncertainties. So the all models are not perfect. So each of the models will have those assumptions and the parameters that we fix. For example, for if we could fix a parameter like permeability or porosity. So these are the parameters of the soil or the geology which are not certain. So we cannot be sure that it can have a particular value. So there will be parameter uncertainties, right? And also there will be assumptions in the model as the model will be assuming the flow as a uniform flow. or the model may be assuming that it is a lumped, when we deal with lumped model, the spatial heterogeneity is assumed. So these assumptions will be there. So uh, that will be quantifying, or that will be creating a model uncertainty. So these every model, every heterological model or every algebraic heterological variables will be what to say, will be related with something called uncertainty. So there's a need to quantify this uncertainty. And also when we make decisions, like when we have a lot of data with us, we could do some statistics and then we can come up to different conclusions about the data, right? For example, I think it will be clear by this time, it will be clear what is a population, what is a sample. Those things will be very clear to you, right? So population is nothing but an infinite series, or not infinite series, like it is a sample space of infinite values. Like if you take the rainfall that has happened in the earth for a very long period, from the very starting period of the earth to the till now, or in the future, that data is called a population, right? So it is very much like a non-realistic or hypothetical. So it is really hypothetical, something that we call as a population, right? For example, the rainfall at Delhi, in a particular location in Delhi is this much. So that the average rainfall that in Delhi is this much. So this can be average annual rainfall of Delhi is this much. Okay, so this can be derived from 10 year of data that we are having, 20 year of data, 30 year of data, 50 year of data, 100 year of data. So these all are like samples. So we have a samples of what we call, like we have different samples of the rainfall that has occurred for 10 years, 20 years, 30 years, 100 years. So these, from using these samples, we try to describe the data, like the what is a for this 30-year period, what was the mean rainfall for this 30 years period, what was the what we say, what was the uh, variability of the data, right? Or how much variability was there in the rainfall, and so on, right? So these are, we are trying to come up with a way, statistical way to describe the data. That is basically called a descriptive statistics, right? So we are trying to describe a data set, for example, rainfall, with the samples which we are having, with the samples, with the help of different statistical measures like the measure of central tendency, that is mean, median, mode, etc., and measure of variance or spread, that is by variance, standard deviation, and all, or even simple way to measure the spread is range, right? And there can be the measure of pickedness, that is using the like kurtosis and kurtosis coefficient, and by the measure of symmetry, with we measure using the skewness coefficient. So these are different ways to describe a data set, and it is called descriptive statistics. It is one part of statistics that is used to describe a random data, or data which are related or which are accompanied by uncertainty. Similarly, there is another field, another subfield called inferential statistics. So inferential statistics is something where we deal with the population, right? So the population, as we already know, it is something hypothetical. We are like assuming things about that. We are trying to come bring out some inferences about the population. We are not determining what is the population, what will be the mean of the population. We are trying to hypothesize, or we are trying to what we say, draw inferences about the population with this different samples of data we are having. So that particular field is called inferential statistics. Right. So in inferential statistics, what we do is we have a sample with us that belongs to one particular population. We can having multiple samples also. Through these multiple samples, we hypothesize that our population mean will be this much. Our population mean will be greater than this much. The variability of our sample, variability of the population variable will be less than this value. The variability is less greater than this value. So these are some hypotheses that we make on our population, and we try to test them using the samples we are having. So we do some hypothesis testing using the samples that we are having, and we come up with a what do you say, with some inferences or conclusions that can be state that as these conclusions are statements like our population can have would be having a mean greater than this much value. But these statements are not deterministic. These statements we are making with some confidence interval. Like with 95% confidence, we can say that the mean of the population will be greater than this value. Still, we are keeping a 5% chance that there can be a failure, right? So that is what that particular subfield is called inferential statistics, where we are trying to draw inferences about the population, which is known to us with the help of the sample data. Other thing that we will be dealing more today in this particular lecture is called the descriptive statistics. Descriptive statistics, that is with the available samples, we are trying to describe a data. So if we have a rainfall data set with you for 10 years, if you just take the mean and tell the mean rainfall adjustments, that is not enough to describe the data set, right? That is only a one measure, it is a one type of measure for the central tendency. So to have a complete description of the data set, we need the measure of central tendency, that is mean, median, or mode. We need the spread of the data, that is a measure of spread, that is through variance or standard deviation. We need the skewness of the data, whether it is symmetric, whether it is skewed to the larger values, whether it is skewed to the smaller values. More skewed means more numbers of values are coming in the towards larger values, or more numbers of the values in the sample are coming towards the smaller values. So that skewness, or whether they are equally distributed, that skewness has to be also to be measured and stated. And also the pickedness, whether the peaks, it is a flat peak or it is a steep peak. So these are different measures which we can together use to describe a data set. So instead of just saying the mean rainfall is this much, if we could state that it is a rainfall at this particular location has this much mean, this much variance, this much spread, this much skewness, and this much what do we say, pickedness. So these all together we will describe the entire data set. So that is called the descriptive statistics, and we will be trying to cover this topic of descriptive statistics in this particular lecture. So mainly it is more statistical. This particular lecture will be more like a statistical, and we will be trying to bring in more questions that are related to hydrological field, where the questions where the variables are mostly hydrological variables, and also yeah, if you have seen my previous lectures, the pattern which I follow was first we start with six MCQ questions and then we go for six NAT questions, that is numerical answer type questions. The MCQ questions were basically to brush up the concepts, and then we can directly jump to the numerical questions where we are actually applying those concepts and solving. And it would be like it was like a practice for you to solve the assignment questions and also for your exams. So in this particular lecture, as the theory part is the concepts are very much already explained in the lecture. So there is I have not put a separate section for the theory. That is, there won't be much MCQ questions. We will be directly solving what we say. We'll be directly solving the numerical questions, and then around 18 or 19 numerical questions are there. So we will be directly dealing with the numerical questions in this particular section. So while we solve these numerical questions, we will be also dealing with the what we say the brushing of the concepts also. Okay, so we can start with the first question. So the first few questions are simple, what we say, probability, basic probability. So only thing that you need to understand would be like the what we say total probability rule. So these are and the sum of all the probability of all events, all even in a particular sample space is equal to one. So those are the very much basic things, right? and how we can get an idea, relate the probability concept with the Venn diagram. So if such questions, the initial few questions, if you could come up with the Venn diagram, it would be very much clear to you. Okay, so this is the first question. Uh, a field is irrigated using the sample using a supply from either canal or groundwater. So there is a field that is irrigated, and the supply is from either canal water or groundwater or rainfall. So there are three possibilities. The irrigation can be due to canal water, can be due to groundwater, or due to rainfall. At any given time, the probability of failure due to inadequate water supply from at least one of these sources is zero point 0.4. So the failure of any of the water sources, either canal water or groundwater or rainfall. So any of probably that any one will fail is zero point 0.4. At least one of the sources will be inadequate. That is zero point 0.4. Assuming the probability of failure of canal, groundwater, rainfall individually are. So each one can fail individually by these values 0.2, 0.05, 0.025 respectively. So information so the informations on the simultaneous failures are as follows. So the probability of simultaneous failure of canal water and groundwater. So both canal water and groundwater will fail. That probability is zero point 0.1. Probability the failure of canal water and rainfall is zero point 0.01. Probability of simultaneous failure of canal water, uh, canal supply and rainfall is zero point 0.3. Okay, so what is the probability of simultaneous failure of all the sources? So, what is the probability that all the sources, all the three sources are failing? So that is what we need to uh, identify, right? So, basically, from this question, it is very much clear there are three events are possible. That is failure of what we say canal water supply, failure of groundwater supply, failure of rainfall supply. So we can take that as three different events, right? So we can name the events E1 as failure of canal supply, E2 has failure of groundwater source, and E3 has failure of rainfall source. So basically that means no rainfall. These are the three events that we are considering. E1 is failure of canal, E2 is failure of groundwater, E3 is failure of rainfall. That is no rainfall, right? So from the given, so we can write what all are given. So probability of E1. So individual failures were already given, right? Probability of E1 was given as zero point 0.2. Probability of E2 was given as 0.05, and probability of E3, that is probability of failure of rainfall, was given as 0.025. So the individual failures were given 0.025, right? So we got the individual, we have with us the individual probability of failure, and the joint failure of, so in the A, B, and C, we're giving the joint failure of two simultaneously, right? So probability of canal and groundwater, that is E1, E2, that is P joint failure we can write. So canal E1 and E2, that is intersection, right? E1 and E2 will fail is zero point 0.01, and probability of E2 intersection E3, that is groundwater and rainfall, not rainfall, that is 0.01, and probability of E1 intersection E3, that is both there is canal supply will be failing and also rainfall sources. There will be no rainfall. That probability is 0.03. Right. So these are given in the questions. And also one more thing is given. So in the so the second sentence, that is, at a given time, the possibility of failure due to inadequate supply of water from at least one of the sources. So the probability that any one of the source can failure. So that is probability of failure of canal supply or groundwater sources or rainfall sources. Right. So or we would be putting for and we'll be putting intersection and or we'll be putting union. Right. So the next thing that is given to us is probability of E1 union E2 union E3. So that is given as 0.4. Right. So now using the union theorem, probability of E1 union probability of E2 union probability of E3 is given as probability of E1. So this should be familiar to you. Probability of E2 plus probability of E3. Then we have to subtract the intersections. Probability of E1 intersection E2 minus probability of E2 intersection E3 minus probability of E1 intersection E3. And then while we subtract the intersections, we will be subtracting twice the intersection of all the three. So that we need to add. So P of E1 intersection E2 intersection E3. So basically, in the question, they has been asked us to find the probability of simultaneous failure of all the sources. So that is basically given by, so the probability of failure of all sources, that is what we need to find. That will be given as probability of E1 has to fail and E2 has to fail and E3 has to fail, right? So that is this particular term. So this particular term is something that we need to find. All other terms, if you see, it is already given the question. It is simple substitution now. So then just substitute these values. This is 0.4 minus zero point 0.2 plus 0.05 plus 0.25 minus 0.1 minus 0.01 minus 0.3 minus P of E1 not minus, is plus E1 intersection E2 intersection E3. So from this we can get probability of failure of E1 and E2 and E3 has, if we solve this, we will be getting it as 0.31. Okay, so this is the final answer. So, so probability of failure of all three sources simultaneously is equal to 0.31. This is a straightforward question. The only thing we need to understand the total probability question, that is E union E1 union E2 union E3 is equal to E1 plus E2 plus E3 minus the intersections of two failures occurring. While we subtract this intersection, we will be subtracting the total intersection of all the three twice. So we need to add that, right? That is the equation that you need to remember. Or if you could draw the Venn diagram, then it will be clear to you. So next we can move on to the second question. Okay, so this is the second next question. So this is also the first few questions will be related to the basic probability theorem. If you are good with the Venn diagrams, you can have an idea. If you could imagine or if you could draw the Venn diagrams and get it is very much clear. Otherwise, we can directly use these equations and also solve it. The probability that a rain gauge instruments at a station A, so it is related to rain gauge at a station A and B will function uninterruptedly for 20 months is zero point 0.8 and zero point 0.9. So there are two rain gauge stations, station A and B, and the probability that they will function for 20 months without any failure uninterruptedly, that is zero point 0.8 and zero point 0.9. Zero point 0.8 for station A and zero point 0.9 for station B. Proper functioning of the rain gauge instruments is independent. So they are both are not dependent on each other. That doesn't like if A fails, it doesn't mean that B can fail, right? If they are not connected, they are working independently. If B fails, A cannot fail. It may not, A can fail or cannot fail. So they're independent. Okay. So find the probability that in the 20 months, both neither at least one will be functioning. So we need to find the probability in the 20 months period, uh, both will be functioning, neither will be functioning, at least one will be functioning. So this is the question. So hope it is clear. There are two stations, two rain gauges. The individual probabilities are given and also they are independent, it is mentioned. So we need to see probability that both will be functioning without any issues. Neither will be functioning without any issue, and either A or B will be functioning without any issue. Okay, so we can solve this. So consider we'll be considering A and B as events that engage instrument function uninterruptedly for 20 months at station A and B. So we can take two events A and B. So we are considering two events A and B. So event A, so there are two events A and B. So A we can say station A rain gauge working uninterrupted in 20 years, 20 months. And B is the event that station B rain gauge working uninterrupted in 20 months. Right, so we have defined the events. That's the very first step we need to do. Now we can write the probability, right? Thus we can write, so P of A, probability that A will be functioning for 20 years without any failure is zero point 0.8 and P of B is 0.9, right? So now we can come to the first part, that is probability of both will be in function. The probability that both A and B will be functioning in the 20-year period. So that will be P of A intersection B, right? P and B should function. So we have to go with intersection, right? So here we'll be applying one of the property, that is if two events are independent, if they are independent, then P of A intersection B is given by P of A into P of B. This is applicable only when two events are independent, right? So when two events are independent, we can write P of A intersection B is equal to P of A into P of B. So we already know what is P of A and P of B are. So we just have to multiply it, 0.8 into 0.9. So that is equal to 0.72. So the probability that both will be functioning is 0.72. So here, what you need to remember is this particular thing, that is P of A intersection B can be P of A into P of B when the events are independent, right? Next is, so the B part is probability that neither will be in function. Probability that neither will be in function. So that is how we can write it. So we can write it like P of A complement. A complement means opposite of A. That is A one function and P of B complement. Intersection P of B complement. That is A failure and B failure. Right. So that is means neither will be functioning. Right. So A complement. So this also A and B are independent. So we can write it as P of A complement P of A complement into P of B complement, because both are independent. A, B are independent, so their complements are also independent. So this would be A complement is 1 minus 0.8, right? And B complement is 1 minus 0.9. Here, probability of A complement will be 1 minus P of A. So we have applied this particular equation. Okay. And so if you calculate this using, we will be getting it as 0.02. Okay. So the probability that both neither will be functioning is 0.02. And the final third part is probability that at least one will be functioning. One will function. So this probability, how we can find. So if you check the first A part, it is both will be functioning. So inverse will be at least one will be functioning, right? So no, actually at least one, the inverse of this will be nothing will be functioning, right? If at least one is functioning is what we need to find. The inverse of this or the complementary of this will be neither will be functioning, right? So we can say this as this will be equal to 1 minus probability of neither will be in function. So that is 1 minus probability of A complement intersection B complement, which we already found in the previous question, right? So that will be 1 minus 0.02, that is 0.98. So the probability that either of them will function is 0.98. So here the idea that we applied is the probability that neither will function, its complementary is at least one will function, right? So that is 1 minus neither will function. Okay. So if that is clear, so we can move on to the third question. That is, for the probability of occurrence of rainfall on a particular day in monsoon is 0.4. So probability that rainfall will occur in a particular monsoon day is zero point 0.4. That is one thing that is given. The probability of occurrence rainfall on two consecutive days. So probability that rainfall will occur in two consecutive days is zero point 0.1. Today and tomorrow, both consecutive days probability that rainfall will occur is zero point 0.1. What is the probability of occurrence of rainfall on 26th July given that the rainfall occurred on 25th July? So it is given that probability rainfall has already occurred on 25th July. It is given to us. And with that condition, they are asking us to find whether the probability of occurrence of rainfall, the probability of occurrence of rainfall on 26th July. So this is something called the concept of conditional probability that we would have seen, right? So here one condition is given. The condition given is that on 25th it was already rainfall. 25th July it's already a rainy day, right? Then they are asking whether it is a rainy day on 26th rainfall. So the condition is already given. And these are monsoon months only, right? The monsoon is basically JJAF, like June, July, August, and September. So this is a monsoon month. And we know the probability that rainfall a day in a monsoon can be a rainy day is zero point 0.4. That is also given. So here we can start by defining the events. So if the events are clear, then it is very much straightforward. So we can write let x, I'm calling it as x and y now, x and y be the events. So we are defining the events of x and y of occurrence of rainfall on 25th and 26th July. So x is the occurrence of respectively. So X is the occurrence of rainfall on 25th July and Y is the event of occurrence of rainfall on 26th July. So this is how we are trying to define the events. So what we need to find is probability that occurrence of rainfall on 26th. So that is Y. Y given. So this is conditional probability. Then we write it as with the slash, right? Given the condition is that 25th was a rainy day. Given X. So the meaning of this is probability that 25th, 26th is a rainy day, given that 25th is a rainy day. So this we can write it as probability of X intersection Y. So this is the formula for condition probability. Probability of X given X is probability of X intersection Y divided by whatever is in the condition. So condition is probability of X. So you can remember this formula where basically what we are doing, we are dividing the intersection probability. We are dividing the probability that both will be happening by the given condition. The given condition has already happened, so that probability we have to divide it. So that the resulting probability will increase. So that is the idea. So basically, the numerator, if you see here, it is that probably on 25th and 26th rain, it will be rainy day. That is a numerator. That is P of X intersection Y. The denominator is nothing but it is already mentioned that 25th is a rainy day. So that probability we are dividing it so that the resulting probability, so that chance we are dividing it so that the resulting probability will be very higher because today is a rainy day, there is high chance that tomorrow is also a rainy day. That is zero point 0.1. The two consecutive rainy day probability is already given 0.1. So it is already known to us as today. So there should be an increase in probability that tomorrow is a rainy day. It is not like today rainfall didn't happen. So it is not like that. Whether tomorrow rainfall happened. Today rainfall has already happened. So that we have having more confidence now that tomorrow will be a rainy day. Okay. So P of X intersection Y is both 26 and 27. So that is two consecutive day rainfall is happening. So that is 0.1, right? Is already given. Given divided by probability of x, that is 25th. So any day being a rainy day, the probability is zero point 0.4 divided by 0.4. So it is 0.25. Right. So you understood the concept, right? So if we are not given that probability that any of the monsoon day can be a rainy day is zero point 0.4. That is not known to us. We only think that we know probably that two consecutive day can be a rainy day is zero point 0.1. Okay. Then if the same question comes, we will be reporting our answer as zero point 0.1 because we know two consecutive days being a rainy day is zero point 0.1, right? But we also know for a particular day to be a rainy day is zero point 0.4. So then if we are given that today it rained, what is the probability tomorrow? Then it shouldn't be zero point 0.1. We should be saying it with some more confidence, right? That is why we divided it with zero point 0.4, and now our probability of occurrence of rainfall on the next day has increased to 0.25. So that is the idea of conditional probability. Okay. The denominator is always the probability of the non-event or which has already happened. Okay, so in that way you can remember. So that is a question related to conditional probability. Now we have a lengthy question. Seems lengthy, but the answers will be very short. So while solving these questions, you can keep keep in mind these all are related to hydrological variables. So these probabilities which are already given in the question, this is something that we need to quantify. For the question's sake, it is already given. So probability that a particular monsoon day is a rainy day is zero point 0.4. How we got that? So we need a data of monsoon rainfall days, non-rainfall days. Then we will be deriving this. So we need to derive samples we need to collect and we have to do some data analysis and do some statistics and come up these probabilities. These are playing with these probability values to derive some other probabilities like occurrence of two consecutive rainfalls. These are derived from like a secondary processes. The primary process you have to understand is we need to, like a hydrologist, we need to derive these probabilities. That is the probability that tomorrow can be a rainfall, today is not a rainfall. So that is something we need to derive from the data, not from the values that are given the question. We have to collect the rainfall data for that location from the rain gauge station. We need to convert into to our format and then we need to fit the probability distributions and then we from that we need to calculate all this. Okay, so we can come to the fourth question, that is an embankment may fail either due to releasing of excess water from the upstream reservoir or due to heavy rainfall or due to simultaneous failure. There is an embankment, say a dam. So it can fail due to excess water from the upstream. So that is the problem when extreme rainfall comes, right? The water reservoirs gets filled up very quickly. And if it goes above the limit, it can collapse, right? So we will be slowly removing water, right? Excess of upstream water comes or due to heavy rainfall or simultaneous. So either can be some the water in the reservoir has increased, upstream water, what excess water is coming in the upstream. That can, if there is a what we say, there is a dam in the upstream of this particular dam. In this particular embankment, there is another dam in the upstream, and there is some rainfall happening there, so they opened the upstream dam. So a large amount of water is coming to the downstream dam, right? So that may cause the failure. That is the excess water or the particular location where the dam is there heavy rainfall is happening. That can also increase the inflow. That is another probability of failure. Or both can happen. That is the upstream dam is also open and here also rainfall is happening. Right. The probability of failure of excess water released from the upstream is 0.01. So excess water from the dam or something from the above, that is 0.01. The same due to heavy rainfall. So the heavy rainfall, the dam can be failure. So these values you can see they are very small, right? So we have to keep it in very small probability, and in that way we are designing the uh, dams, embankments, and all, because it is rarest of the event or can only cause the failure. Even that cannot shouldn't cause the failure. In that way, we are designing these embankments or dams and all. However, probability of failure of embankment due to excess release during heavy rainfall is quite high and estimated as 0.5. So the probability of failure of embankment due to excess release during heavy rainfall, that is both happening together. There is an excess release coming from the upstream and also heavy rainfall is happening. That is estimated to be quite high and 0.5. So these both happening together, the probability of failure is more, 0.5. So you understood the question. Now we have to determine probability of failure of the embankment. Probability that embankment will fail. It can be either due to the upstream water, excess water coming, or due to heavy rainfall. So both. That is the first question. The second question is probability that failure due to heavy rainfall only. That is excess release from the upstream. Uh, this way we are not considering. There is no excess release from upstream. So only rainfall is happening in that particular embankment upstream. Okay, so this is the two things that we need to see. So same procedure. First, we will clearly define the event so that it won't make any confusion. So first, I'm calling the events as E and R. So let E and R represent the events of failure due to excess water release from upstream. So that is the first event E, and due to heavy rainfall, that is R. Due to heavy rainfall is R. Due to heavy rainfall respectively. Okay, so it is clear two events E and R. E is due to excess upstream inflow and R is due to excess rainfall, right? So E and R is already given to you. Probability of E is 0.01, it is given, and probability of R is also given as 0.08. And zero point 0.5, what is 0.5? That is, however, the probability of failure of embankment due to excess release during a heavy rainfall day. That means it is a heavy rainfall day that is already given to you, right? However, the probability of failure of embankment due to a excess release during a heavy rainfall day is quite high. That means it is a heavy rainfall day that is already given, and the embankment will fail due to excess rainfall. That is nothing but P of E given R. It is given that it is a heavy rainfall day, then the probability that it will fail due to an excess upstream inflow coming is 0.5, right? So now we can come up with the first part, that is probability of failure of the embankment. So probability of failure of embankment, it can be either due to both. That is, we can say probability of failure, we can say, right? Failure, that is equal to probability of failure due to embankment failure, or it can be due to excess rainfall, heavy rainfall. That is P of E plus P of R minus P of E intersection R. So P of E intersection R we need to find, right? So we can make a substitution there. That is P of E plus P of R. These both are given. So from the conditional probability equation, P of E intersection R, we can write it as P of E given R into P of R. Right. So from the conditional probability equation, we can write this. Next is the substitution. P of E is 0.01, P of R is 0.08 minus 0 of E given R is zero point 0.5 and P of R is 0.08. So this will be coming around 0.05. So this is the probability of failure of the embankment. It can be either due to the failure of failure by excess upstream flow or due to failure of excess rainfall or heavier rainfall. Now we can go to the D part. That is probability of failure due to heavy rainfall only. It will fail due to heavy rain. There is no excess inflow coming in from the upstream. Okay. That is, we can write it as probability of R, that is failure due to excess rainfall intersection with E complement. That is no excess excess inflow is coming from the upstream. Okay. So this we can write with the conditional probability equation. We can write E complement given R into P of R. Right. So P of E complement given R we can write as 1 minus P of E given R. Right. So that into P of R. So 1 minus P of E given R is 1 minus 0.5 into 0.08. So that would be 0.04. So this is the probability of failure due to heavy rainfall only. The idea is what we need to find is P of R and E complement. That is R will occur and E won't be occurring. And the intersection that can be written as P of R E complement given R into P of R, that is the conditional probability equation. Then P of E complement given R, we can write as 1 minus P of E given R, right? Then into P of R, so this just substitution, then we'll be getting this particular answer. So, hope it is clear. Now we can move on to the next question. There are several industries located on the bank of a river. Okay. It is observed that the waste from those industries are mixing into river without proper treatment. So without proper treatment, the river streams are getting polluted. The water supplies are collected every day from two different sections, 1 and 2 of the river to check the pollution level. Let X denotes the event that the event is already defined that the pollution is detected in section 1 and Y denotes the event that the pollution is detected in section 2. Following information is obtained from the laboratory test. So P of X is given and P of Y, the probability that the pollution occurs from the section 1 is 0.158 and pollution occurs from the is detected in the section 2 is 0.25. And the probability that at least one section is polluted, either one or two, the union, right, point is 0.27. Determine the probability. So we are given these values, we need to determine the probability that section 1 is polluted given that section 2 is already polluted. Section 2 is polluted given that section 1 is already polluted. So these are this direct continued, what we say the conditional probability cases, right? So we can directly write what is given. So P of X is given as 0.158 and P of Y is given as 0.25, and P of X union Y, X or Y is 0.27, right? So from the from this we can write P of X union Y is equal to P of X plus P of Y minus P of X intersection Y, right? So from this we can find P of X intersection Y is given by P of X union Y minus P of X minus P of Y. So this actually this will be the opposite, right? Signs will be changed. Plus this will be a minus, right? So minus 0.27 plus 0.158 plus 0.25. This, when you solve, you'll be getting it as 0.138. So we got P of X intersection Y. Both X and Y are polluted. Section A, X and Y, we did a pollution that is given by 0.138. Okay. So now we can come to each case. Case A is probability that reach 1 is polluted given that 2 is already found polluted. Okay, so that is P of X given Y. That can be P of X intersection Y divided by P of Y. So this formula is very clear. 0.138 divided by 0.25, that is equal to 0.552. So that is the probability of reach 1 is polluted given that reach is already polluted. And also probability that reach 2 is polluted given that 1 is already found polluted. So that probability is nothing but P of Y given X, that is P of X intersection Y, that remains same. The denominator will change, P of X. So that would be P of X intersection Y is 0.138 divided by P of X is 0.158. So this will be around 0.873. Okay, so these are direct conditional probability cases where we just need to find the intersection X intersection Y. We are given with X and Y and X union Y. If we get the X intersection Y, we can find the conditional probability P of X given Y and P of Y given X. Okay, so that is done. Now we can move on to the sixth question. Okay, the number of rainy days in a week of December at a location is found to be following. So number of rainy days in a week. So it is number of rainy days, right? So we are coming to probability distributions now. So in that case, if you could remember the lecture, we saw there are what is a random variable, that is first thing we show. The random variable is something that variables that comes with some randomness. So that is, these are the variables that we define to use to define the probabilities. So rainfall can be a random variable. Number of rainy days can be random variables, right? So These random variables can be of two types. One is discrete random variables and one is continuous random variables. So these examples, which I just said, that is a number of rainy days that are they are discrete. They are integer values like one, two, three. They are discrete values. And for example, or the maximum rainfall or the rainfall magnitude at that particular location. So these rainfall amount. So these are continuous values. They can be decimal. So these are called continuous random variable. So first we will be discussing about discrete random variables, and discrete random variables probability we call it as PMF, that is probability mass function, right? And for continuous random variable we call the probability distribution as PDF, that is probability density function. Okay, one is probability mass function, that is for the discrete random variables, and the other is the probability density function, that is for the what we say, that is for the continuous random variables. Okay, only that needs to be sure, that needs to be clear, and next we can follow. So week has 7 days, and it is in December, and number of rainy days in a last week of December, it is near dry day at a location is found to be the following. So PXX is basically probability. So this PX, so how we represent it is probability is denoted by small p, and the random variable we represent it by capital X, and the values it can take we represent as small x. Okay, so the representation of the PMF, that is probability mass function, or PMF. Okay, so PMF. So evaluate, so what we need to, so they are defined the PMF, that is when x is equal to 0, that is no rainfall days or no rainy day, the probability is C. So C is a constant that we need to find. And when the prob x is equal to 1 to 7, so number of rainy days can be maximum 7 only, right? Minimum 1, minimum 0, and maximum 7 in a week. So there the probability is given by e raised to minus 1 by 2 by x. 2x, e raised to minus 1 by 2x. So that is the expression for probability. For each x, it will be having a particular discrete probability value. And elsewhere, if x is greater than 7 or less than 0, we have 0. Okay, so evaluate the C for the PXX to be a valid PMF, and the probability of more than two rainy days in the last week of December. So there are two parts. First, we need to find C so that PMF can be a valid PMF, and then we need the probability for more than 200. So we can solve this. So first we can start with the definition. So x is a random variable, so it is not mentioned, so we can mention it here. X is our random variable. So let us consider x to represent the number of rainy day. So that is our random variable, discrete random variable in the last week of December. Okay, so this is the what we are defining x as our random variable has a number of rainy day in the last week of December. So the value of C can be evaluated like the total probability should be, so this should be 1, right? Here the total probability, since it's a discrete case, it is will be addition. So for all I, the summation of for all I, Px, sorry, it is small p, capital X, small xi, should be equal to 1, right? So this we can write it as, we have to add for all i's. So when I equal to 0, the probability value is C. When I equal to 1 to 7, then when I equal to 1 to 7, I equal to 1 to 7, the probability value is e raised to minus 1 by 2x. Right, so that is not I, x is equal to 1 to 7. Okay, and this sum should be equal to 1. Then we can write our C as 1 minus summation of x equal to 1 to 7 e raised to minus 1 by 2x. So that will be 1 minus 1 by, so this we can take out, right? 1 minus e raised to minus 1 is a constant, and also 2 is a constant. 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7. Right. So if you substitute this, we'll be getting C has 1 minus 0.477. So C is equal to 0.523. Right. So probability of C means probability of no rainy day in the last week of December. That is 0.523. Okay. So this is defines our PMF. We found what is C also. So next question is, and it is a valid PMF now because total sum of all will be equal to 1. Now the second part of the question is probability of, so second part is the probability of more than two rainy day. So this is will be nothing but P of X is a random variable greater than 2. More than 2 means greater than 2. Let's not mention more than, greater than, or equal to, just greater than 2. So that will be P of 3, 4, 5, 6, and 7. So that we need to add, right? But it is difficult to add. There are like 4 many terms. So we can do one thing. We can say take the complementary of the opposite. That is 1 minus P of X less than or equal to 2. That is a complementary. So 1 minus, that will be P of X equal to 0 plus P of X equal to 1 and P of X equal to 2. Right. So now it is just substitution. 1 is 1 minus P of X equal to 0 is C that we just found out, 5, 2, 3 plus P of 1 is e raised to minus 1 by 2 and P of 2 is e raised to minus 1 by 2 into 2. So if you substitute this, we'll be getting it as 0.201. This is the final answer. So probability that there can be more than 2 rainy day is equal to 0.201. Okay. So this is how we deal with PMF, probability mass functions for discrete random variables. Now we can go for a continuous random variable case. It is question 7. Right. So the annual maximum discharge at a gauging station follows the following distribution. So there is the random variable is, earlier it was discrete because it was number of rainy days, right? It was a number, but here it is maximum annual discharge at a gauging station. So that is discharge meter cube per second. So that is some continuous value. It can be decimal. It is a very continuous value, right? So for x is greater than 1, that is maximum discharge greater than 1, it is given by 1 by x square and elsewhere it is equal to. So here we represent x, f, capital X our random variable and small x the values the random variable can take. So that we call it as probability density function. Okay, so it is called probability density function of PDF. Earlier it was PMF, probability mass function for the discrete case. Now we are dealing with PDF, that is probability density function. Okay, the question is the distribution of the maximum annual discharge is given at a given station. Evaluate the probability of maximum annual discharge greater than 5 unit and probability of maximum annual discharge between 2 and 10 units. So these are straightforward questions. This is just integration, right? So we can start with the first part. So the A part is probability, the probability of annual, sorry, not rainfall, annual discharge of annual discharge greater than 5 units, right? So that will be P of x greater than 5. So we can write it is that, so either we can write it or we can make use of the concept of cumulative distribution, cumulative probability. Cumulative probability, which is denoted by capital F, that is cumulative density function, CDF, that is always when the value is less than or equal to this particular value. Okay, so that is, you can mention P of F where x is 5. So instead, we can add one more step that would be better. That is P of x less than or equal to 5. When we mention probability of x less than or equal to some value small x, we can write it as that is a cumulative distribution function when of x equal to x, the random variable x is equal to x, right? So this we can write it as probability, sorry, 1 minus probability, not probability, that is cumulative distribution function of x equal to 5. So that will be 1 minus integration of p of x less than or equal to 5 is 0, minimum value is 0, right? No, p should be is greater than 1, so the minimum value is 1. 1 to 5, PDF is 1 by x square, 1 by x square dx. Okay, so if you solve this, it will be 1 minus x raised to minus 2 plus 1 plus 2 plus 1 within the limit 1 to 5. If you substitute the limits, finally we'll be getting it as 1 by 5. Simple integration, so you'll be getting it as 1 by 5. Let's save more space here, so it will be coming out as 1 by 5. And we can go to the this 1 by 5 is something equal to zero point 0.2, right? Now we can go to the second part, B, that is probability of annual maximum discharge between 2 and 10 units. That is P2 less than X less than 10. This we need to find, right? So this can be PF, that is cumulative distribution function of, or instead we could write like this also. P of X less than or equal to 10 minus P of X less than or equal to 2. That is, we are taking the total probability from 1 to 10, then we are subtracting from 1 to 2. Whatever left is something between 2 and 10, right? So this we can substitute it as integral 1 to 10, 1 by x square dx minus integral 1 to 2, 1 by x square dx. So this is direct integration. You can solve this integration. It will be this, the first term will be coming around 0.9 and the second term will be coming around 0.5. You can just check. It will be 0.4. That is the probability that the annual discharge, maximum annual discharge will be between 2 and 10 units is coming out to be zero point 0.4. Okay. So I hope it is clear. This is a question with where we introduce PDFs, that is probability density function. Okay, so we can move on to the eighth question. So consider the following sample for annual peak discharge. So we have a annual peak discharge in QMAC. So we are given with the sample now. So we are given with the sample and at a given station A, we are given with the sample of the annual peak discharge. So the values we are given with, okay, the measurements we are given with. Evaluate mean, variance, coefficient of skewness, coefficient of kurtosis. So these are the things we need to evaluate. We need to evaluate the mean, variance, skewness, coefficient of kurtosis. Okay, for the given sample. Also comment regarding the skewness and kurtosis. Okay, so basically this is where we tackle the concept of descriptive statistics. So we are being asked to describe the annual peak discharge. The annual peak discharge in QMAC at a gauging station A, we need to describe the data set. So we are given with a sample of annual discharges from 2000 to 2015. So with this 16 years of data that we are having, we need to describe. So here, how we will be describing is that we will be using the measure of central tendency, that is mean. We said that mean average discharge is this much, the variance of discharge is this much, the skewness of first pass is this much, that is whether it is positively skewed, whether it is negatively skewed, and the coefficient of kurtosis, whether it is the distribution is a uh, picked one or a flat one. So this is how we describe a data set when we are given with a data set. How we describe the data set. Okay. So that is a descriptive statistic. That is what we are going to do here. So mean it would be very clear to you, right? We are given with a sample. So we are given with a sample. So sample mean we denote it by x bar. Right. Sample mean we denoted by x bar. So mean is nothing but summation of I equal to 1 to n xi by n. So you can take a note of the what do you say, take a note of the values you want. So this is the formula for mean or the average. Okay. So that would be 2630 plus 2662 plus 1931 plus 3655 plus 3670 plus 4005 plus 4621 plus 1557 plus 2405 625 6216. That was a flood year. Then 2602 plus 2157 plus 3120 plus 6403, another flood year. Then 2934. So these are the discharge values that we need to divided by n. N is 16 years we are data we are having, right? 2000 to 2050. So if you solve this, it will be coming around 3385.93 cubic. Okay, so the mean average maximum annual discharge, peak discharge at that particular station A is 338.93. Okay, that is the central measure. Central tendency is the values are centered around this particular value, that is 338.93. Okay, so next is variance. So we got the mean. Now we can go for variance. So variance, sample variance, we denote it by S square. S square is the standard deviation and S square is the variance. So summation of I equal to 1 to n xi minus x bar the whole square divided by n minus 1. So this is the formula for sample variance. The n minus 1 instead of n it is n minus 1, that is for a bias correction. So this is whatever we are estimating is for a sample, deviation sample, not for the population. For the bias correction, the bias, there can be bias due to the population. So to remove the bias, we are usually dividing it by n minus 1. Okay. So this can be written as this is equal to 46330, sorry, 4630 minus mean is how much? 3385.93. This all square plus 2662 minus 3385.93 all square plus etc. Similarly, we have to do for each. Finally, we'll be having 2934 minus 3385.93 all square. This would be our numerator, and we'll be dividing all there by n minus 1, that is 16 minus 1, that is 15. So this would be coming around 221,486.86. That is around 2.2 into 10 power 6 cubic square. So this is the variance. This much cubic square is the variance of the 15 or 16 years of data that is given. Okay, so we need more space. So next is skewness. So we got the variance. Next is coefficient of skewness. Skewness coefficient that is represented by CS is equal to N by N minus 1 into N minus 2 into S cube. S is a standard deviation, S cube into X summation of I equal to 1 to N xi minus x bar the whole cube. So basically, the mean we can is the first moment about the origin. So we are taking the first moment about the origin, then we will be getting mean. Variance is the second moment about the mean. That's why xi minus x bar the whole square we're taking. Skewness is nothing but the third moment about the mean. That gives skewness. Okay. So we just have to substitute here. So it is n square, sorry. So n square means it is 16 square divided by 15 into 14 into, sorry, it is not 16 square, it is 16 only. N by n minus 1 and n minus 2. 15 to 14 into 2. So we got our variance as 2214,860.86, right? So that is variance square. S cube means raised to 3 by 2, right? By 1 by 2 it will be x, then we have to cube it. That into, then we have to do the summation, that is 4630 minus 33. It is about the mean, that is the third moment about the mean. The whole cube will be coming, so then 2662 minus 3385.93 whole cube. So on up to it will be 2934, the final term, minus 33, the mean is 85.93, the whole cube. Right, so this is the denominator. So if you solve this, the entire thing, it will be coming at around 0.745. So what we can say about the skewness? The skewness is value of, this is positive. So skew CS is positive. 0.745 is positive. So data, we can say the data is positively skewed. Okay. And now for fourth question, fourth part. That is for kurtosis coefficient. K, K is divided by K, that is n square here, n square will be coming divided by n minus 1, n minus 2, and n minus 3 into s raised to 4, standard deviation raised to 4. Then the summation term, that is summation of I equal to 1 to n. It is the fourth moment about mean, xi minus x bar whole raised to 4. That's the fourth moment. So if we substitute this, we'll be getting it as 16 square, that is known. Numerator will be 15 into 14 into 13 into variance is 221486 whole raised to square. Then it will be 4, right? And that into the numerator. Now the summation terms will be 4630 minus our main is 3385.93 the whole raised to 4 plus 2662 minus 3385.93 whole raised to 4 plus so on up to 2 plus 2934 minus 3385.93 whole raised to 4. So if you solve this, when you solve this, this will be you can write it here only. This would be coming around 2.268. So this is our kurtosis coefficient. Okay, and our k is less than 3. So we call this as, there are different ranges. You can refer some standard textbook. So if its k is less than 3, we call it as platyphotic. Okay, so this is how we describe our data set with whatever data set we are having. We describe the data set, we describe the central tendency, find their variance, find their skewness, find their kurtosis, and finally we define or describe the entire data set with these statistics. Okay, so now we can move on to the ninth question. So ninth question is the number of thunderstorms per year. So here also x is a discrete random variable, right? Last question we are discussing we're discussing what's a continuous random variable. Now it is also number. Thunderstorm years in a year and its PMF is obtained by from a historical data as shown in the following table. So we have this table. So this table is having PMFs for different uh, number of thunderstorm years. 0 number of year, the PMF value is 0.3. For one thunderstorm year, one thunderstorm per year, that is zero point 0.4, two thunderstorms per year, 0.2, and three thunderstorms per year, it is 0.1. What is the mean and variance of the number of thunderstorms in a year? So we need to find the mean and variance. That is expectation of X. Right. So we are given with, so we will be given with the PMF. We need to find the mean and variance. How we can find the mean and variance of the X. So basically, X is nothing but under of thunderstorms, right? So expectation of X is given by summation of X P X, right? So that will be 0, X is 0, right? X into P of corresponding P of X is 0.3 plus 1 into 0.4 plus 2 into 0.2 plus 3 into 0.1. So that will be coming around 1.1. So 1.1 thunderstorm per year. That is the mean thunderstorm. That is 1.1 thunderstorm per year. That is the expectation of number of thunderstorms per year. And the variance for this same can be calculated. So V of X for the same can be calculated if the PMF is given. It can be calculated as expectation of X square minus expectation of X the whole square. So this is the formula to find the variance, expectation of x square minus expectation of x the whole square, right? So expectation of x square will be summation of x square pxx minus, this is already we have calculated 1.1 square. So that will be 1 square into zero point 0.3. No, it is 0. First one is 0. That will be 0 is 0 square into zero point 0.3 plus 1 square into zero point 0.4 plus 2 square into zero point 0.2 plus 3 square into zero point 0.1, right, minus 1.1 square. So if you solve this, you will be getting our variance as 0.89. So it is very straightforward. If we are given with the PMF to find the mean and variance, and as to find for mean, that is expectation of x is given by the expectation of x uh, sigma xp of x, and variance is given by expectation of x square minus expectation of x whole square. Then we have to just substitute the substitutions, and we'll be directly getting. Okay. So now we are given with a PDF. So earlier it was a PMF. So now we are given with a PMF and a PDF, that is probability density function, that is a continuous random variable. The random variable is rainfall depth. The rainfall depth received during a thunderstorm at a place X is it's a random variable with the following density function. So it is a random variable and X is rainfall depth. So it is a continuous random variable and we are given with a PDF. Okay. Determine the mean, median, standard deviation, coefficient of variation, and skewness coefficient. So these are the coefficients that we need to find. Okay, we can start the same. We will be same following the same formula, but only thing is that we say continuous random instead of summation we will be using integral. Okay, so A is mean and mean mu will be given as integral 0 to 10. So x varies from 0 to 10, right? X, f, x, x. dx. This will be giving us our mean. So the constant we can take out, that is 3 by 2500 integral 0 to 10 x into x minus 10 into x minus 20 dx. Okay, so this would be 3 by 2500 into, if you integrate it, you will be getting it as, so before that we can just expand it so that it's really easier for us to integrate, right? So 3 by 2500 into, within the integral we can just expand it, right? 0 to 10, so x into x square minus 20x minus 10x plus 200 dx, right? This we can further simplify as 3 by 2500 integral 0 to 10. So x, if we take it inside, it will be x cube minus 30x, that is 30x that it is minus 10 minus 30x square plus 200x dx, right? So we can write this as x cube will be x raised to integrated x raised to 4 by 4. So minus 30 x cube by 3, right? X cube by 3, and this will be becoming 10. And finally, plus 200 x square by 2. So this will be 100. So, and the limits of integration was 0 to 10. To substitute this, we'll be getting it around 3. So the mean of annual rainfall depth, that is annual rainfall depth mean, is coming out to be 3 or 3 centimeters. Okay, so next we can move on to another measure of central tendency, that is median. Okay, so B, that is median, that is mu and D, we can say. So median is that particular value, that is, it is the central value, right? That it is a central value which that divides it into two halves, each having equal probability. The left half will be zero point 0.5 and right half will be also zero point 0.5. So that is a middle value. The middle value, which either side will have equal probability 0.5, zero point 0.5. So integral 0 to mu d f of x dx, this is the probability of this particular range will be 0 0.5. So 0 to mu d 0.5, then mu d to the other extreme will be also 0.5 because the total probability is 1, right? So in this way, we can solve for median. So here, what we can do is, so we can substitute for this. So 3 by 2500 integral 0 to mu median x minus 10 into x minus 20 dx will be 0.5. Okay, so we can substitute, so we can expand this. So this will be 3 by 2500 integral 0 to mu d. Inside the bracket, it will be inside the bracket it will be x square minus 30x plus 200 dx, right? That will be equal to 0.5. So now we can further solve it. 3 by 2500 into x cubed by 3 minus 30x square by 2 plus 200x within the limit 0 to mu d is equal to 0.5. So it is direct substitution now, that is 3 by 2500 mu d cube by 3 minus 30 mu d square by 2 plus 200 mu d is equal to 0.5. The zero terms will be cancelled. So when you solve this particular, uh, basically this is a, what we say, uh, a polynomial with degree 3. So you can solve this using the calculator. Then we will be getting mu d, that is median, to be 2.5398. So there, along with this, there will be another two solutions because it is a cubic variable, right? So there will be another two solutions. So we will be selecting that which lies in our range of x. So our range of x is between 0 and 10. So our x should lie between 0 and 10, right? So our median should be also between 0 and 10. So with that criteria, we'll be eliminating other two solutions and we'll be selecting this particular solution. Okay. So we have done with median and mean and median. So these are the two measures of central tendency. So another thing that we can compare the mean and median value, the mean was coming around 3 centimeter and our median is coming around 2.583 centimeters. So they are not same, right? They are not same. The mean value and the median are not same. So, uh, so here, one thing I wanted to highlight is when we can another these there's this two different measure of central tendency, right? One is mean and one is median. So which would be the better? Which is which? How can we say this is a better for what we say better measure for the central tendency? Either why whether we go for mean or either we go for median. So that is so I can give an example. Take a case where in a particular location the rainfall is within the range, the daily rainfall is within the range of, let's say, two, right? For example, the daily temperature, if you take it as an example, temperature is in a range of, uh, say, 20 to 25 degrees Celsius. And some erroneous measurement came, and one particular data is going up to what we say 40 or 45, or one heat day occurred or outlier occurred. So when we take the average, so this higher value, one single higher value will be having a greater influence and it will pull the mean upwards to the near to the 40. But actually, the location was receiving for a long time around 20 to 35 or 20 to 30. It was not going till 40. Only one measurement was there, which was one day was there where the temperature went to 40. But it will give as a wrong impression that this particular location is around having a temperature on an average every day it will be around 35. But actually the temperature for that particular location is around 20 to 25. Right. So in such cases, if we go for median, the median will be less influenced by the one single value, so one or how we call it as outliers. Okay. So the medians, if you go with median, then this one particular outlier coming, it won't be having that much influence. Okay. So in such cases, we can go for median instead of mean when there is more outliers in the data. Okay. So next is standard deviation. Standard deviation. Okay. The standard deviation, how we can find is, so we represent a sigma square that will be integral 0 to 10 x minus x bar, that is the second moment about the mean, f x x dx, that is 3 by 2500 integral 0 to 10 x minus x bar is 3, we already know, the whole square into x minus 10 into x minus 20 dx. So you can do the simplification. When you do the simplification further, after integration, it will be coming around. So 1 by 12500, 3x raised to 5 minus 135 x raised to 4, okay, plus 1945 x cube minus 11025 x square plus 27 double triple zero x within the range 0 to 10. Now, if you apply the limit, this would be coming out to be 5 centimeter square. So, this is the variance. So, standard deviation will be sigma will be root 5, that is 2.2361 centimeter. Okay, so we got our spread also. So the spread is 2.23 centimeter. Mean is 3, median is 2.593, and the spread is 2.3. Spread about the mean is 2.361 centimeter. Okay, so next is coefficient of variation. So coefficient of variation is straightforward. It is CV, it is represented by CV. It is just the ratio of our standard deviation and mean. So how much and it's represented in percentage into 100. With respect to mean, how much is the variation? So it is very high. No, variation is coming around 2.361. This much difference is there, and mean is our 5. So that will be around 74.5 percentage. So this much variation is there about the mean. About the mean, 74.5 percentage of variation is there. So that is, I think, very large. And finally, uh, the last part is skewness. Skewness coefficient, gamma. So it is it is the uh, third moment about the mean, 10 raised to 10, x minus mu, the whole cube, f x x dx. So it is a coefficient, then we have to divide it by sigma cube, right? So for a discrete case, we already found that this will be 3 by 2500 into 5 root 5 So that is sigma cube. Then integral part will be 0 to 10 x minus 3 the whole cube, then x minus 10 into x minus 20 dx. Right. So we can solve this. It will be coming around, if you expand this and then integrate, this would be coming around 25140 root 5 into x into 10x raised to 5 minus 468 x raised to 4. It's a simple integration only. Just you have to expand it and you have to integrate. There is much, not much complicated integration coming. 740 x square plus 186,300 x minus 324,000,000 to 10. That is our limit. So if you substitute those values, you will be getting it as 0.7155. So this is the, what we say, this is the coefficient of skewness. Okay. So here also the coefficient of skewness, so gamma is greater than 0, it is positively skewed. Okay, so this is how we find the descriptive statistics for if you are given with a continuous random variable and its corresponding PDF, right? So it's almost time. So there are further questions. There are like around 10 more questions. So what I will be doing, so I have requested for an extra section this week on the coming Thursday. So if that slot is assigned, so I will be taking up these questions. So these questions are now, it will be mainly on the extreme value distribution, that is our Gumbel distribution and extreme value problems, and also related to our frequency analysis. So these 10 questions are left. So I have requested a section for 2 hours on this coming Friday, coming Thursday, same time, that is 6 to 8. So in that section, we can continue with the rest of the 10 questions and we try to finish it off. And finally, we'll be having our final class, that is week 12 section, we'll be taking up on next Monday. Okay, so if you have any further doubt in this particular class or anything related to the assignment or anything, you can contact me. My name is Akhil J and my contact email is Akhil Naradevan, AKHIL JNANADEVAN at gmail.com. Okay, so I'm closing this section. So thanks for watching my video.